All right, we want to prove the power rule for derivatives. Now, if you take in a first year calculus course, this is one of the first derivative rules that you learn after computing derivatives using that nasty limit definition. So let's remind ourselves what the power rule says, that if we have x to the nth power and we want to compute the derivative, that's going to be equal to n times x to the n minus 1. And in order to prove the power rule, we're going to need this piece right here to help us, which is the binomial theorem. And the binomial theorem says if we have a binomial raised to the nth power, in this case x plus y to the nth power, that's going to be equal to the sum. So this weird looking e thing, this is a Greek letter called sigma. This means just basically add a bunch of things. So this is a shorthand way of saying add. So we have the sum from k equals 0 all the way up to n. So k is our counter or our index, and n is our upper limit. And then we have this weird looking thing right here. This is n choose k. So let's write this down. This is n choose k. And what n choose k means, this is the number of ways to pick k objects given n objects, and we're going to assume that k is less than or equal to n, where order doesn't matter. Okay? And then we multiply that by x to the n minus k times y to the k. And this is how we would expand this binomial x plus y to the nth power. All right, and then one more time, n choose k is the number of ways to pick k objects given n objects where order does not matter. All right. So let's go ahead and prove this. So using the limit definition, we're going to have f prime of x equals the limit as h approaches 0 of x plus h to the nth power minus x to the nth power, all divided by h. Now, we can immediately use the binomial theorem to help us out. And we're going to expand this piece right here. All right, so we start at k equals 0, and then we're going to go all the way up to n. We won't write out every term. Okay, we'll only write out a few terms because if we write out every term, that would be very tedious. So for the first piece, we're going to have the following. N choose 0 times x to the n minus 0. But n minus 0 is just n, so we're going to have x to the n. And then h to the 0, that's just equal to 1, so we can get rid of that. Plus n choose 1, because we're at k equals 1 now, times x to the n minus 1. And then we're going to have h to the first power plus dot, dot, dot. And then we're going to go all the way up to n choose n. And then we're going to have x to the n minus n, but that's going to be x to the 0, which is just 1, so we can get rid of that piece. And then we're going to have h to the n. All right, and then minus x to the nth power, and then all divided by h. All right. So far, this is what we have. Let's just start simplifying some things. So n choose 0. So let's focus on this piece right here. So n choose 0 means the following. So given n objects, how many ways can I choose 0 objects given n objects where order does not matter? And there's only one way to do that, and that's by doing nothing. So n choose 0 is actually just 1. All right? N choose 1, so how many ways can I pick one object given n objects where order does not matter? Well, that would be n ways. You just pick every singleton. So n choose 1 is going to be equal to n. And then how many ways, let's focus on this last piece here. How many ways can I pick n objects. Given that I have n objects where order does not matter, well, there's only one way to do that. You would just pick all of them at once. So n choose n is going to be equal to 1, and then we would get some other values here for the intermediate terms. However, we don't necessarily care what those values are specifically. Okay, so let's go ahead and continue. So this is going to be equal to the limit as h approaches 0 of x to the n plus n times x to the n minus 1, and then times h plus dot dot dot. And then we're going to have h to the n minus x to the n, all divided by h. Now, we see that we have x to the n here, and we have minus x to the n. So those pieces are going to disappear. And then notice, all right, when we expand our binomial x plus h to the n, what's happening is that these powers of h, right, originally we had an h to the 0 here, and then we have h to the first power, and then somewhere in here is an h squared and h cubed, dot, 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 and then we have an h to the nth power. So all of these terms, except for the first term, right, has at least one factor of h, okay? Because remember, h to the 0 is just 1. So we can actually get rid of this. And let's get rid of this too. So let's go ahead and reduce each factor of h in the numerator by 1 and get rid of this h downstairs in the denominator. So let's go ahead and do that. So this is going to equal the limit as h approaches 0 of n times x to the n minus 1. This h is going to disappear, so you're not going to have this h anymore. And then we're going to have plus dot, dot, dot. So all the intermediate terms that have an h in them are going to they're going to be reduced by 1 power. And then we're going to have h to the n minus 1. And then let's put some parentheses here because now we have a sum. All right. Now we can go ahead and plug in 0 and see what happens because we got rid of this h in the denominator after we reduce every power of h in the numerator by 1. So when we do that, we're going to get that this is equal to n times x to the n minus 1. So we copy and paste the first piece and bring it down because there's no h's in there. And then remember all these intermediate terms that are within these dot, 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 dots and this h to the n minus 1 have at least one factor of h. So all of these pieces, right, are going to go to 0. And then what will remain is just this piece right here, n times x to the n minus 1, which is the power rule that we know. And that concludes the proof. I hope you all enjoyed.